Hi, this is lecture 7 part 4. In the previous segments we discussed about random variables and distributions. We also came to know about binomial distribution formula and geometric distribution formula. Then we used this formula to determine the distribution of random variables. In this segment we will know about expected value of random variables. Like always, let's start with a simple example. The question: let the following table shows the marks obtained by 50 students in CSE230 post mid viva. Okay, so this is the table showing the marks of 50 students. What is the expected marks from a random student of the class? This is the question. So you see that 3 students got 20 out of 20, 13 got 15, 20 got 12, 10 students got 8, and finally 3 was obtained by 4 of the students. So in total there are 50 students here. Now, what is the expected marks if we choose a student randomly? If you think that the expected marks of a random student whose marks is unknown to you is the average, then you are right, because that makes sense, right? If you don't know someone's marks, then from the idea of the marks obtained by the students, you can say that he might be getting some marks which is average of the class, right? So how to determine the average of these marks? I think all of you know how to determine the average or the arithmetic mean of these marks. First, we have to determine the sum of the marks of 50 students. Here you see 3 students got 20, therefore we have added 3 20s and then 13 15s and so on, right? And then we can write 20 times 3 plus 15 into 13 plus 12 into 20 plus 8 into 10 plus 3 into 4. So this is the total marks obtained by 50 students of the class together. Now the expected or the average marks from a random student is sum divided by the total number of students in the class. So finally we get the average, which is 11.74. So this is the expectation from any random students of the class. All right, let's solve the same problem in slightly different manner. So we are sharing the same table here. The table shows marks obtained by 50 students again. Suppose X is the set of a random variable that is defined as the numbers obtained by the students. Find the distribution and expected marks from a random student. There are 5 different marks obtained by the students, and they are 20, 15, 12, 8, and 3, right? So this is the random variable set X. What would be the corresponding probability for each of these random variables? We can say that if a student is randomly chosen from the class, what is the probability of the students to get 20? That is the corresponding probability for 20, right? So we can write 3 by 50 here. How? There are 50 students in total and 3 of them got 20. Therefore, 3 by 50 is the probability of some student to get 20. Similarly, we can say that 13 by 50 is the probability of someone to get 15. 20 by 50 is someone's probability to obtain 12 marks. Similarly, we can write 10 by 50 for 8 and 4 by 50 for 3, right? Now I'm going to do something and the reason will be explained after it's done. So if we multiply each of the variables to its corresponding probability, we will get something like this, right? Okay. So if we calculate the value, we will get 11.74, exactly the average of the students' marks. How so? Let's see the previous form of the solution. This was the sum, and then finally we got the average to be of this form. And then if we distribute this denominator to each of these terms, we will get 20 times 3 by 50 plus 15 times 13 by 50 and so on. Okay, see exactly the same form we got here. Therefore we can say that for a set of random variables, if we multiply each of the variables to its corresponding probability and add all of these products together, we get the expectation or the expected value of this random variable set. Okay, 11.74, it means that this is the marks or this is the expected value of this random variable. Okay, so expectation or expected value is the average of the random variables. So this expectation or expected value can be referred as average or mean or first moment or mathematical expectation. All of these terms are synonymous to expectation or expected value. Expectation of x is denoted by e of x or mu. The following is the distribution of a random variable set x, where x1, x2, x3 are random variables inside x, and the corresponding probabilities are listed here below each of the variables. Then e of x equals to the sum of the product of each random variable with its corresponding probability. Now we know that e of x is also denoted by mu, and this is the summation form of the formula. One thing I want you to note is the sum of all of these probabilities will be equals to 1. Okay, so yeah, this is written here. Now let's go see some example. Suppose you are rolling a die. X is the number that appears. Find e of x, or find the expectation from a roll. So if you keep rolling a die, what is the average score expected from each of the rolls? That is something I'm interested in. To solve it, first we have to determine the set of the random variables. If we roll a die, then 6 outcomes are possible. 1, 2, 3, 4, 5, and 6. Now the corresponding probability for each of these results would be 1 by 6, right? This is simple. And therefore the expected value of x, e of x, would be 1 times 1 by 6 plus 2 times 1 by 6 plus 3 into 1 by 6 plus 4 into 1 by 6, 5 plus 6 into 1 by 6. We take 1 by 6 as common. Yes. So for the sum of first 6 positive integers, we are going to use a formula. I hope you know that. The sum of the first n positive integers, 1 to n, equals to n into n plus 1 divided by 2. Famous mathematician Carl Friedrich Gauss discovered this formula at a very young age, and there is a nice story behind it. So I hope you've heard it, or you can Google it just to see the proof of this formula. This is very easy. So the sum can be written as 6 times 7 divided by 2 using the formula. So we'll get it like 3.5. So 3.5 is the expected score from each of the rolls. That doesn't mean if you keep rolling a die, 3.5 will always show up. Rather, it means if we roll the die for a large number of times and keep record of scores, then the average we see on a single roll will be close to e of x. Okay, so if we keep rolling the die and keep records of the scores, then the average score for a single roll will be close to e of x, or the expected value. All right, so 3.5 is the expected value. Now my question is, if we roll the die for 4 times, what would be the expected total? You know that the expectation from each of the roll is 3.5. Therefore, after rolling 4 times, the expected total would be 4 times 3.5, which is 14. Okay, so 14 is the expected score for every 4 rolls. Let's give you a similar exercise to solve. The question says that in a game of Scrabble, the point value of a randomly chosen Scrabble tile has the following distribution. Okay, so in Scrabble you can get 0, 1, 2, 3, 4, 5, 8, or 10 from each tiles, any of these scores, and the probability for you to have each of these scores is listed just below the variables. Okay, so the question is, what would be your expected point value if a tile is randomly chosen? So if you choose a tile randomly, what would be your expectation? And the next question is, what would be the expected total after you have chosen 7 tiles randomly? I think you can solve it. So let's see another example. The statement is, suppose Bangladesh is playing against Pakistan in a 7-match series. The team that wins 4 matches first wins the series. Once a team wins the series, there's no next match. Let X is the number of matches required for the series to end. Find the expected number of match in the series. Hence, you have to determine the expected number of match required for the series to end. Now, to solve this, we know that it may take 4, 5, 6, or 7 match for the series to end, right? Because it's a 7-match series, and if any of the team wins the first 4 matches consecutively, then the series will end. So it can take 4, 5, 6, or 7 matches for the series to end. Therefore, X has 4, 5, 6, and 7 in it. Now, to determine the expected number of matches in the series, we have to find the distribution first. Now, see, this is the table, and we don't have the probabilities now. So for 4 matches, we can consider there are 4 free boxes, and if all 4 of the boxes are filled up by either B or P, then we can say that yes, the series will end in 4 matches. Now, what is the probability that all of the first 4 matches will be won by Bangladesh? It's simple, because if you consider there's no draw, then the probability of Bangladesh to win the first match will be half, second half, third half, and fourth half. Therefore, the probability would be 1 by 16. Similarly, for Pakistan, the probability would be same. So it's 1 by 16 as well. Now, finally, we can say that the probability of the series to end in 4 matches equals to 1 by 16 plus 1 by 16, right? We got it from P of C1 plus P of C2. Okay, so it's 1 by 8. So this is 1 by 8. Let's put 1 by 8 here. And again, let's go to the next case, which is for 5 match. What is the probability? So this is the tricky part of this problem. Listen very carefully. Like 4 matches, we have 2 cases here. Case 1 would be Bangladesh wins the series in 5 matches, right? And case 2 will be similar for Pakistan. So we know that if we determine the probability of case 1, multiplying the probability by 2 will give us the sum of both of these cases, right? Because both of these probabilities are same. So we are going to calculate the probability for case 1 first. Now, if we want the series to last 5 matches and Bangladesh to win the series, then among the first 4, Bangladesh needs to lose 1, right? Otherwise, the first 4 consecutive win will end the series within 4 matches, right? We don't want that because we calculated the probability here. So we are going to use the binomial distribution formula in a slightly improvised way. That is, we have to choose any one of the first 4 boxes where we want Bangladesh to lose. In other words, we want Pakistan to win in any of the 4 matches. Okay? So let's say we're going to choose 4C1 where we want Pakistan to win. Therefore, say we have chosen this box and we are going to put P here. So the probability of putting a P in this box would be half, right? Now we are left with 4 boxes, 1, 2, 3, and 4. And all 4 of these are to be occupied by B. Therefore, we are going to choose all 4 of the free boxes for Bangladesh. So for each of the boxes, the probability for Bangladesh to win would be half. So the power would be raised to 4, right? So the probability is 4 times 1 by 2 to the power 5, 1 by 8, right? So similarly, the probability for Pakistan to win the series in 5 match would be 1 by 8. Therefore, P of C1 plus P of C2 would be 2 times 1 by 8, which is 1 by 4. So we have already put this probability here. Now for 6 match, what would you do? For 6 matches, we have similarly 2 cases. One for Bangladesh win the series in 6 match, another for Pakistan win the series in 6 match. If you consider 6 free boxes here, you have to note that in the first 5 matches, 2 must be lost by Bangladesh. Otherwise, the series will end in 5 match. Okay, so from the first 5 match, I have to choose any 2. Say I have chosen these 2 boxes where I want to put P, and the probability for Pakistan to win 2 matches will be half squared. And then we are left with 4 boxes again, and we want all 4 of these matches to be won by Bangladesh. So we have to choose 4 out of 4, and for each of the match, the probability for Bangladesh to win is half, so half to the power 4. This is the probability of case 1 for 6 match. Okay, so 5C2 equals to 10, and it's half to the power 6, so 1 by 2 to the power 6. Therefore, 5 by 32. So 5 by 32 is the probability for Bangladesh to win the series in 6 matches. Similarly, for Pakistan, the probability will also be 5 by 32. Therefore, P of C1 plus P of C2 would be 2 times 5 by 32, which is 5 by 16. Okay, so let's put the probability here, 5 by 16. And for 7 match, we have to do similar calculation. The probability we're going to get is 5 by 16 again. Okay, so try it yourself. And let's check if all of these probabilities add up to 1 or not. So 1 by 8 plus 1 by 4 plus 5 by 16 plus 5 by 16. If we add all of these fractions, we will get 2, 4, 5 plus 5, which is 16 by 16. Yeah, it's 1. That means our calculation is correct. So we were interested in determining the expected number of matches for the series to end, right? Now, all we have to do is multiply these variables with their corresponding probabilities and then add all of the products. So we will get 4 times 1 by 8. This is, say, E of x. Tell me, who is this person? Plus 5 by, sorry, plus 5 times 1 by 4, 6 times 5 by 16 plus 7 times 5 by 16. So this is the expected number of match till which the series is supposed to last. Okay, so 5.8125. So the prediction says that on an average, such 7 match series are supposed to last for 5.8125, which is nearly 6 matches. All right, so I hope you understood the basic of expectation. If you want to see a similar example, you can go check example 1.18 from Rigdor's elementary probability. The problem is called a roulette problem. So now we are going to see another example. So example 3 was a problem that was discussed in lecture 7 part 3, where the question was, suppose the probability of success in a single experiment is P. You are running the experiment repetitively. X equals to the number of trials required for a success. Find the probability distribution for X. So we solved this problem and finally the distribution was found like this. And now my question is, what is the average number of trials required until one success? Now we are going to determine the expectation of this random variable set, which means on an average, how many experiments are required for you to meet success for once. To solve it, we're going to determine E of x again, and we know the formula. So E of x, or mu, equals to summation of I equals to 1 to, yeah, this would be n, 1 to n xi pxi. So each of the random variables are going to be multiplied by the corresponding probability, and then we are going to sum all of this product. Now we are putting the values of xi, which is I, because it can start with 1 and go up to infinity, because it might take infinite number of experiments to reach success for once. So I, and the corresponding probabilities would be of this general form, p into 1 minus p to the power I minus 1. Now upon calculation, we will get that E of x equals to 1 by p. To see the rigorous proof of this theorem, you can go to example 1.3 of chapter 1, read to Red's elementary probability. There is a simpler way to state that with a simple example. Okay, suppose you are rolling a die and you know that the probability of getting a 6 is 1 by 6. Okay, so p of 6 is 1 by 6, where let's say p of 6 means the probability of rolling a 6. This 1 by 6 fraction can be explained in a different way like this. If you do the experiment 6 times, you can expect 1 6 out of it. Okay, so to get 1 6 on an average, you have to perform the experiment for 6 times. Now if we define success as getting a 6, then you see that the number of experiments required for one success, which is rolling a 6, equals to 6 on an average. So it states that on an average, in every 6 experiments, you will be successful for once. Now see, this 6 actually came from 1 by 1 by 6, right? Which means 1 by p. So this is the expected number of experiment, which is mu equals to 1 by p. Let's see an example. The question states that what is the mean number of rolls required to get a 1 from a die? This is exactly like the problem we just have discussed. So what is the mean number of rolls, or what is the average number of trials required to get a 1 from a die? Okay, so let probability of rolling a 1 with a die equals to 1 by 6. We are denoting it by p, and p equals 1 by 6. We know that. Therefore, the mean number of rolls required to get a 1, which is denoted by mu here, equals to 1 by p by our formula, and we just have explained it in a different manner. So equals to 1 by 6, which is 6. That means on an average, you will need to roll a die 6 times to get a 1, right? So yeah, that's it. In the box, we explained the formula mu equals 1 by p. That means if the probability of success in an experiment is p, then the average number of trials required for one success would be 1 by p. Let's see example 2. It states that 5 men play a game of odd man out to determine who will pay for the pizza they ordered. Each of them flips a coin altogether. If only one person flips a side opposite to the all remaining 4, like 1 heads, 4 tails, or 1 tail, 4 heads, then he is the odd man and he has to pay for it. Otherwise, they'll flip again. The question is, what is the expected number of tosses needed to determine who will pay? To solve this problem, you need to keep in mind that first we have to determine what is the probability of success P, which is finding an odd man in a single experiment. Then, to get the expected number of tosses, we will find 1 by P, which is mu. Let's try to determine what is the probability of getting an odd man in a single experiment. Okay, so let's think about 5 boxes. So all we want is put H or T in any one of these boxes, and once the letter is put there, in the all remaining 4 boxes, we want the opposite of the results, right? So case 1 would be 4H1T. So we are going to put 1T in any of these 5 boxes, and then we are going to fill up remaining boxes with H. Okay, so we can choose any one of these 5 boxes for putting a T. Therefore 5C1, say we have chosen this box, and now the probability of getting a tail from this turn or this box would be half, right? We are using binomial distribution formula, and from the remaining 4 we can choose all 4 of them, which is 4C4, and or we can omit this term because 4C4 equals to actually 1. So in those 4 boxes we want 4 heads. So we want 1 minus half. If we write it like this, the probability of not getting a tail, then we want it to happen for 4 times. Therefore the final probability would be 5 by 32. Okay, so for 4 tail 1 head we'll get exactly the same result. Therefore it will also be 5C1. This half is coming from 1 head now, and then 1 minus half to the power 4, which is also 5 by 32. So if any of these 2 cases happen, either C1 or C2, we will find our odd man. Therefore the final probability P would be P of C1 plus P of C2, which is 5 by 32 plus 5 by 32, which becomes 5 by 16. It's pretty much similar to our Bangladesh-Pakistan cricket match problem, right? So now this is the probability of finding an odd man in a single experiment. All we have to do now is just inverse this probability to get the expected number of tosses required for getting an odd man out. So this 1 by P would be 5 by 16 to the power minus 1 equals to 16 by 5, which will be 3.2. It's not possible to run 3.2 experiments, right? Because it's a fraction. Therefore, we have to say on an average, we will need 4 experiments to find an odd man from this kind of scenarios. So imagine after 4 of the experiments, suppose we have found our odd man out. What will be the look on his face being so unfortunate to pay for all 5 of them? You want to see? This is him. Okay, so I think most of you know him. Anyway, for similar problems, you can see example 1.24 from Rick Duret's elementary probability, which is called China's one-child policy. Now for a bet, you are going to see a few examples on your example class on bet. So for a bet, if E of X is less than 0, then it's a gamble. Okay, so when the expectation is negative, then you can call it a gamble. If E of X or mu equals to 0, that means it's a fair bet, and if E of X is greater than 0, then it's a sure win. Okay, So you are going to need this idea to solve a few problems in future, and the examples on it are provided in lecture 8. Now the expectation function E has the following properties. 1. If x has a discrete distribution and y equals to r of x, then E of y equals to summation of r of x times p of x equals to x. So if you're interested in the proof, then check theorem 1.2 from Duret's probability book. We're going to solve a few problems on it. Example, roll a die once. X equals to the number that appear, find E of x squared. Since x equals to 1, 2, 3, 4, 5, 6, therefore x squared would be the square of each of the variables, right? So 1, 4, 9, 16, 25, 36. Now to determine the expectation of x squared, you have to know the corresponding probability for each of these elements, right? Now what would be the probabilities? Are the probabilities anywhere related to the probabilities of the variables of x? Yes, they are. Now the probability for each of the elements of this capital X, which is denoted by small x, and the probability for each of the elements in x squared, which is denoted by small x squared, both of these probabilities will be same. Just consider it like this. Say there is a die with 1 square, 2 square, 3 square, 4 square, 5 square, and 6 square marked on each of its faces instead of 1, 2, 3, 4, 5, and 6. Now, would the probability of rolling 3 square be different from probability of rolling a 3? Let's see. Say this is the spatial die where this face here has 9, the face here has 4, and it's 1. So you see that each of the faces would have a square number. So therefore the invisible faces will have 16, 25, and 36 dots on them respectively. Now you know that despite variables on each of its faces have been changed, the number of faces remained same, which is 6. Therefore, the probability of rolling 2 square would be 1 by 6 again. Because there are 6 regular faces and each of them are equally likely to show up. Therefore, the probability of rolling a 2 square would be 1 by 6. Probability of rolling a 1, which is 1 square, would be 1 by 6. And the probability for rolling a 3 square would be 1 by 6 as well. Okay, so we can say that no, it would be 1 by 6 for both 3 square and 3, 4 square and 4, and so on. Just the variables have been changed, but the corresponding probabilities will remain the same, right? So let's see the distribution here. So this is the distribution. So here you see the random variables of x are in the chart, and the variables in x squared are also written here, and the corresponding probabilities for each of the variables remain same, which is 1 by 6 for all of them. Therefore, E of x squared would be summation of x squared, p of x equals to x, right? So we are going to use property 1 to solve this problem, where we stated that if y equals to r of x, then E of y would be E of r of x equals to summation of r of x times p of x equals to x. Okay? So yes, finally we're going to put r of x equals to x squared in the problem, and all p of x's are 1 by 6. Therefore, it would be 1 into 1 by 6 plus 4 into 1 by 6 plus 9 into 1 by 6 plus 16 into 1 by 6 plus 25 into 1 by 6 and 36 into 1 by 6. Now, taking 1 by 6 as common, we have 1 square plus 2 square plus 3 square plus 4 square, 5 square, and 6 square, right? Now, for the sum of first n square numbers, we know the formula would be 1 square plus 2 square plus 3 square up to n square equals to n into n plus 1 times 2n plus 1 divided by 6. This is a formula you saw in your high school, so we are going to use this formula, or you can just manually put the values in calculator and calculate them. So finally, the result would be 6 times 7 times 13 divided by 6 using the formula here. So finally, it would be 91 by 6, which is 1516. Okay, so 15.166 is the value of E of x squared. Now there are some other properties of E. The property 2 is E of x plus b equals to A of x plus b. So if you want to see the proof, you have to go to the book again, but we can explain it in an easier way, right? If 1 is added to the numbers on a regular die, okay, then E of x plus 1 would be 2 into 1 by 6 plus 3 into 1 by 6 up to 7 into 1 by 6, right? Each of the variables are increased by 1. If you calculate it, you will get the value 4.5. Now you see 4.5 is 3.5 plus 1. Now we got 3.5 as the expected value of a regular die, which was E of x. So it's E of x plus 1. So finally, we just proved that E of x plus 1 equals to E of x plus 1. Similarly, we can prove E of ax equals to a E of x. But we are going to need these properties for studying variance. To have an idea about the degree of difference between the random variables and the expected value, we use variance. So variance is a measure of spread for a distribution of a random variable that determines the degree to which the values of a random variable differ from the expected value. Okay, so square rooting the variance, we get standard deviation. Both of these terms are frequently used in discrete mathematics and statistics. So the formula that we are going to use to determine the variance in these problems is this. Variance x equals to E of x square minus mu square. Sometimes it's also written like E of x square minus E of x whole square. Okay, so we know that mu and E of x are used alternatively. Note that E of x square and E of x whole square, both of the terms are not equal at all. In the last example, we saw that if we roll a die, then E of x square equals to 15.166, where x is the number that appeared. And in example 2, we saw the average or the mean number in every row is 3.5. So if 3.5 is squared, we will get 12.25. C E of x whole square, which means mu square, and E of x square are definitely two different terms. Okay, so if you're interested in the derivation, then see the example 1.25 from Rig-Duret's elementary probability. Now, determination of variance has 3 steps. Step 1 is to determine E of x, which is mu, using the distribution. We have solved a lot of problems on it. Step 2 is to determine E of x square. So we are going to determine x square from x, right? And then we know that for each of the variables of x squared, the probability will be as same as p of x equals to x, right? So we can determine E of x square. Finally, we're going to put these two values, this value here and the value square here, to finally get the variance. There's a few examples on variance worked out in your lecture 8, so watch it. And you can also see example 1.26 and 1.27 from chapter 1 of Duret's book. So our syllabus for midterm ends here. Hope you study well and got a very good figure in the midterm.